All right, so for these notes, we're going over parametric equations, and now we're going to specifically look at things in regards to calculus. So we're going to be looking at derivatives and that sort of thing. So if you guys recall, yesterday we looked at parametric equations where we had x describing a horizontal distance over a given period of time, the y describing the vertical distance or the height over a given length of time, and then we see that our curve, while in relationship to that horizontal distance and that height, we can also pinpoint here's where the time is 0, here's where the time is 1, later on we could say where the time is 2, and so on. So that's our parametric equation. We also know that the object in the beginning, if you look at your notes from yesterday, they said that that object was projected at an angle of 45 degrees. And that angle of 45 degrees in some ways is kind of telling us what our slope is. So this angle right here is 45 degrees. And we want to be able to use that information to kind of figure out what a slope is. So here they said, oh, if it's 45 degrees, then tan of 45 is 1. And the reason they use tan of 45 is because if you recall how to find tan of something, you do y divided by x. And y divided by x should remind you of slope. We've got rise over run. So if you look at rise over run for a 45-degree angle, y divided by x, we're just going to think about triangles here. So if this was a triangle, I made a right triangle here, we would have a 45, 45, 90 triangle, and anytime that's the case, then this side, I'm going to call it S, and this side, they actually have the same length. So now if we think about simplifying tan of 45, then I have opposite over adjacent. The two lengths of those sides are exactly the same. Or we could look at the unit circle and say, what's tan of 45? Divide the y-coordinate by the x-coordinate. Either way, we're going to see that the slope there is 1, which fits. The picture here, it looks like a slope of 1, so that's pretty reasonable. So we want to say, well, how could we find the slope at another time? Because if we know what the initial projection is, then we could always just do tan of that angle and solve for it, and then we'd know our slope. But that doesn't help us over here when the angle has changed and we no longer know what the angle is. So this is when we're going to start to use derivatives, because derivatives represent our instantaneous rate of change. So if I want to find dy dx, dy represents the change in y, dx represents the change in x, and these are instantaneous changes. So to find the change in y, I'm going to find the derivative of y of t, so I'm going to do y prime of t. And to find the change in x, I'm going to do the derivative of x, and so I'm going to say that's x prime of t. So if I wanted to find the slope at any time I wanted to, it doesn't matter any time, then I could take these two equations right here, so in terms of for x and for y, and I could take the derivative of those and divide those, and that would tell me my slope at any point on that graph, right? So if a smooth curve is given where we have x as some function of t and g is another function of t, then the slope at that point is going to be dy dx equals dy dt. So that's the derivative of this one, divided by dx dt. And that's the derivative of this one. And that is as long as dx dt does not equal 0, and that's because we can't divide by 0. So this is important. This is if you want to star it or underline it or make it bold or whatever. That's our kind of like formula. How do we find the derivative? We do the derivative of y divided by the derivative of x, and we're doing that derivative in terms of t. So we're leaving it in terms of t when we're doing it. All right, so next we want to say, how could we find the second derivative? So since dy dx is a function of t, you can repeatedly do this process to find higher order derivatives. So what we're going to do is we're going to replace y in the dy dx equation with dy dx. then we can say if we want to take the derivative of dy dx, so that'll give us our second derivative, then that's going to be the derivative in terms of t of dy dx divided by dx dt. And so that's going to tell us that our second derivative is this stuff. And again, that's kind of like our formula, so if you want to put a box around it or star it or whatever so that it's something you can go back and refer to, that would be good. All right, let's go ahead and flip to page 2. So the first example says, find dy dx for the curve given by x equals sine of t and y equals cosine of t. So first I'm going to find the derivative of x. So the derivative of sine is negative cos. Nope, positive cos. I was thinking integrals. All right, positive cos. The derivative of y would be the derivative of cos, which is negative sine. So dy dx is going to be the derivative of y divided by the derivative of x. And negative sine divided by cos is negative tangent. So that's our general slope there, right? And if we wanted to know the slope at any specific time, then we could just plug in the value for t and we would know the slope at that specific time, or the rate of change at that specific time. All right, find the slope and concavity at the point 2, 3 of x equals the square root of t and y equals 1/4 t squared minus 4. So I'm going to go ahead and just distribute that 1/4. So I've got 1/4 t squared minus 1. So I'm going to go ahead and work with that function. That way I don't have to think about, oh, is that a product rule or whatever, or be confused about the parentheses. I just don't have to worry about it. So the derivative of x, I'm doing this because I want to find my slope. The derivative of x, I'm going to think of this as t to the 1/2, would be 1/2 t to the negative 1/2. The derivative of y is going to be 2/4 t. Well, that's it, just 2/4 t. All right, so to find the slope, we have to find our derivative first. So I'm going to say dy dx equals 1/2 t divided by 1/2 t to the negative 1/2. Okay, so those cancel. That gives me t, what was t over t to the negative 1/2. I'm going to go ahead and take this and move it to the top. So that's t times t to the positive 1/2. And if I add my exponents, that gives me t to the 3/2. So the general form of the slope at any time is t to the 3/2. Now I want to find the slope at that specific point. So I'm going to say the rate of change, the instantaneous rate of change at the point 2, 3. I got to figure out what my t value is first, actually. Go ahead and erase that. So I'm going to go back to those equations. Now you can plug in 2 for x and solve for t. You could plug in 3 for y and solve for t. I'm going to go ahead and plug 2 in for x because it looks a little bit easier to me. All right, so I'm going to say plug 2 in for x. I get 2 equals the square root of t. And then I square each side, I get 4 equals t. So I know at this point in time, the time is 4 seconds or 4 minutes or whatever the units happen to be. So now if I want to know my slope at that point in time, then my slope is going to be 4 to the 3/2. So I'm taking that general equation and I'm plugging in t for this specific moment. So 4 to the 3/2 really means the square root of 4 raised to the 3rd power. So the square root of 4 is 2 raised to the 3rd power. 2 to the 3rd power is 8. So the slope at the point 2, 3 is 8. So it's fairly steep there. All right, the concavity is going to use a second derivative. So I'm going to say this is the work that I did for my slope. Over here I'm doing concavity. So the formula for the second derivative was d2y dx squared is d dt times dy dx, which was t to the 3/2, divided by dx dt, which is 1/2 t to the negative 1/2. All right, so d dt is if I take the derivative of the top part. So it's saying take the derivative in terms of t. So the derivative of this would be 3/2 t to the 1/2 divided by 1/2 t to the negative 1/2. And I can go ahead, I'm going to rewrite that so it's a little bit easier to deal with. I'm going to say that that's 1 over 2t to the positive 1/2. All right, now I can go ahead and flip this up. So 3/2 times 2 is just 3. T to the 1/2 times t to the 1/2 is t to the 1. So that means our second derivative is 3t. Now to find the concavity, I'm going to go ahead and evaluate my second derivative at 4 as well, so at that same time, because we're doing the same point. And so that's going to be 3 times 4, which is 12. Now that 12 is positive, so that means that our graph is concave up. If it was negative, then we would say concave down. So concavity, concave up, and then we're done. All right, third example says, we have this picture, the Prolate Cycloid, I don't know if I'm saying that right, is given by x equals 2t minus pi sine t and y equals 2 minus pi cos t, and it crosses itself at the point 0, 2, which you can see right here. They want to find the equations of both tangent lines at this point. So we have two different tangent lines. We have one where the curve goes to the right, one where the curve is going to the left. So the first thing that we need to do is find the derivative. So I'm going to say the derivative of x is 2. And then the derivative of this piece, the derivative of negative pi sine t would be negative pi cos t. And then y prime would be, the derivative of 2 is 0. And then the derivative of negative pi cos would be positive pi sine t. So that means that our dy dt is pi sine t divided by 2 minus pi cos t. Okay, so now we've done the derivative, kind of like we did with this problem right here. So now if we want to find the slope, that means that we have to know what we're going to plug into our derivative. And we figure out what to plug into our derivative by taking the point. We can take the x-coordinate 0 and plug it in for x. We can take the y-coordinate 2 and plug it in for y. It doesn't matter which one we do. So I'll go ahead and take x again. So 0 equals 2t minus pi sine t. And the goal here is to be solving for t. And I'll go ahead and add the pi sine t to the other side. And I quickly realized that's an equation that I don't know how to solve. Pi sine t and 2t, I'm not sure how to solve that. So I'm going to ignore that one. I'm going to try the other one. Plug 2 in for y. So y equals 2 minus pi cos t. And then I'm trying to isolate the t so I can subtract this 2 to the other side, and that gives me 0 equals negative pi cos t. And then I can divide the negative pi over to the other side, so I get 0 equals cos t. So now I'm picturing my unit circle, and I'm saying to myself, on my unit circle, what value or what angle measurement is going to give me an x-coordinate of 0. And that's going to be up here and down here. So this is an angle measurement of pi halves. This is an angle measurement of 3 pi halves. So I'm going to say that t is pi halves and 3 pi halves. So now if I want to find the slope at those specific points, so this slope right here and this slope right here, then I need to just take that derivative that I found. Oh, up here I wrote dy dt, but I meant to write dy dx. I'm sorry if that was confusing. So dy dx, and I'm going to evaluate that when t equals pi halves, and I'm going to evaluate that when t equals 3 pi halves. So for pi halves, I'm going to get pi times sine of pi halves divided by 2 minus pi times cos of pi halves. So sine of pi halves is 1. So I have pi times 1 is just pi. And then here I've got 2 minus pi times cos pi halves. Well, cos of pi halves is 0. So pi times 0 is just 0. And then for the other one, I'm going to have pi times sine of 3 pi halves. I guess I don't need parentheses there. Divided by 2 minus pi times cos of 3 pi halves. And pi times sine of 3 pi halves would be pi times negative 1. So that's negative pi. And then we have 2 minus pi times cos of 3 pi halves is 0. So negative pi over 2. All right, now they didn't say they only wanted the slopes. They say that they wanted the equation of the tangent line. So if you guys remember back to units towards the beginning, we were using, what was it called? Point slope. We were using point slope form. So we're going to say y minus the y coordinate of the point equals the slope times x minus the x coordinate of the point. So that would be this equation right here with the positive slant. The other equation would be y minus 2 equals negative pi halves times x minus 0. All right, we have one more page of notes. All right, so next we're going to recall the definition of arc length. We're going to be using it. So the arc length is the length of a curve. And it is also known as the total distance that's traveled in particle motion problems. All right, so if x is f of t and y is g of t, and those provide a smooth curve where it does not intersect itself on AB except maybe at the endpoints, then the length of the curve is, so we're giving a formula here for arc length, dx dt squared plus dy dt squared. And you were square rooting that and taking the integral. So this should remind you of the distance formula, which it kind of did last time too. So another way to write this would be x prime of t squared plus y prime of t squared. These equations are identical, it just kind of comes down to the way that you're comfortable writing it. So the last example says, show that the circumference of the unit circle is 2 pi by using the parametric arc length formula. So we want to write a parametric equation for the unit circle. So I just want to remind you guys that when we wrote equations for circles, it was usually x equals cos t, y equals sine t. This is going to be a unit circle because it's going to have a radius of 1. So if you think back to when we were writing these, we would have, like, I guess we did cos squared first. Cos squared plus sine squared equals 1. So I know that cos is x, so that's going to give me x over 1 squared plus y over 1 squared is 1. And so that gives me a circle that is centered at 0, 0 and has a radius of 1. And that's what the unit circle is. It's a circle that's centered at 0, 0 with a radius of 1. So all that is to say, this is how I knew to use this when they said unit circle. So the derivative of x is the derivative of cos, which is negative sine. The derivative of y is the derivative of sine, which is cos. And now I'm finding the arc length. So I'm going to say from 0 to 2 pi, so those are my endpoints, of the square root of the derivative of x squared plus the derivative of y squared. And then I can go ahead and simplify this a little bit. I know that negative sine t being squared is actually the same as sine squared. And this is cos squared. And hopefully that's reminding you of the Pythagorean identity for trig identities. This is actually the square root of 1. So sine squared plus cos squared actually just equals 1. And then, so the square root of 1, I don't need the square root anymore. The square root of 1 is just 1. So when I integrate 1, I get t, and I'm evaluating t at 2 pi and 0. So when I plug 2 pi in, I get 2 pi. When I plug 0 in, I get 0. And so this equals 2 pi. And so there I am proving, using parametric arc length, that the circumference of a unit circle is 2 pi. And we know that, right, because the circumference formula is 2 pi r, and the radius of a unit circle is 1. So 2 pi times 1 would be 2 pi.